Here we go. So yeah, just sorry, getting loaded up there. Welcome back, everyone. We've got Murtaza talking about Mach0 and really the Mach0 binary format, understanding how it works, what the different components of it are, and how that's relevant to attackers and defenders. So I'll hand it over to you. Go ahead, Murtaza.
Cool. Thanks for the intro. So hey, my name's Murtaza Munaim. I'm an engineer on the mobile security team at Square. And I'm here to talk about the Mach0 binary format and kind of what happens when you release an app to the App Store. So quick overview, Mach0 binary format is the main executable file format used on Mac OS and iOS. It's used to store any compiled code you'd see if you're reversing an iPhone app. So it's pretty important to know how to maneuver it and navigate through it. Most people that actually look at apps for a company, or if you're just doing it for fun, you're probably going to look at apps through the App Store. In some cases, you might be given like an enterprise side app or an app that is like private. And so in these cases, it wouldn't come from the App Store, and you wouldn't have some of the technical problems that you would have when looking at apps from the App Store, mainly the encryption. But in 90% of the cases, you will be dealing with things through the App Store. And so I'm going to go a little bit on the details of what exactly happens when you submit things to the App Store and how the actual code looks different. And this is pretty important, kind of from two standpoints, from attacker standpoint and defender standpoint, but I'll get into that later. And so as I stated before, like, why do you want to do this? It's good to know how to navigate the Mach0. It's just good to have fluency. Kind of, I wouldn't say like a diss to ELF, but ELF is a file format maybe more people are familiar with. But Mach0 has an enormous amount of information. It's very descriptive, and there's a lot of things that you can glean from the binary that can help in reversing. And so it's very good. It's important to be able to understand all the different nuances of it. Again, I keep talking about this point just because I kind of do defense for my day job, so it's kind of applicable to that. But knowing about the Mach0 format and how it interacts with the App Store is actually kind of useful to develop like program verification of your app. So if you're trying to develop some way to like ensure app integrity, it might be a little bit counter to what maybe most people are talking about here, but defenders in the room will definitely appreciate the information I present here. Last point, if you're actually RAing stuff from the App Store, you probably should have a good understanding of fair play and how app decryption works and how you can do it. I won't be going into the actual like nitty-gritties of like the key exchanges and like how fair play works, but I'll just go over a little bit about what it is and then actually how to decrypt apps. There's a bunch of different tooling to do that, but I'll just show you like a very simple way that makes sense. So quickly, the Mach0 binary format is like has the core basics are it's like programmed through load commands, and so load commands are kind of the structure that helps represent different aspects of the binary, and each one of these like commands describe how the binary is loaded in memory, but also way more than that. It describes like metadata, and it's very, very useful stuff. And so here's just a quick breakdown of a Mach0 binary. I just outputted the mappings that are used to actually map the code and data into memory. I haven't showed the rest of them, but we can actually go through that in later on. So basically there's a concept of segments and sections. So segments are what are defined by the load commands, and they are what the actual kernel uses to take the piece of segment data and load it into memory. And the sections are what we can see. The kernel uses information from the Mach0 to actually jump into the segment. And so you can kind of like look at the permissions on the segments. So like text is read, execute, data, read, write, linked, edit is a section that might be a little bit interesting, not exactly intuitive, but it's readable only. And they have all different purposes. Text makes sense, has executable code, could be hooked and patched by exploiters and reversers. Data has, you can see it has a lot of like Objective-C sections. And so a lot of like, at least for iOS, well, now there's like Swift, but Objective-C is like one of the languages used to develop iOS apps. And so the data section actually has like the metadata associated with the Objective-C data. And so I'm not totally sure actually why they're in the data section, but I can only think that it's due to swizzling. So in iOS, swizzling is like a first class method to hook your own functions, and it's like totally supported by the Objective-C runtime. And so I'm guessing they're in the data, so the runtime can modify the pointers easily, but otherwise doesn't really make too much sense. Yeah, so I can go quickly if anyone's interested in the symbol resolution. So I just wanted to point out that you guys can like ask questions in the YouTube stream, and then I can try to answer them if I'm going too fast for anything. If you have any questions, please feel free to ask them there. I'll just go quickly over symbol resolution, just real quick. In the green boxes, if people are familiar with like how GOT symbol resolution works for ELF, it was pretty similar in Mach0, but you have like the __symbol stub. And so these are where all the like imported functions stubs are. So there'll be like a call to like access or stat, or any other sort of function that you want to call that's not in your program. And those will always call to some pointer, and that pointer will always be inside the data segment. So the data __ NL or the LA symbol pointer. And it'll point to a value in those sections. And those sections have bytes that are like empty. But when you actually go call that function, the same way in ELF, how the GOT and the PLT have like a stub function that actually resolves the pointer when you actually need it. The pointer in the data segment will actually jump back to the text stub helper. The stub helper will then call out to DYLD, which is like in iOS, it's like a daemon that's used to kind of like the zygote for iOS, and it will try to resolve different symbols, and it does more than that. But so DYLD will then come back and actually write the pointers back into the data segment. And so the next time you actually go and call things from the symbol stub, you don't actually have to go all the way through back to the text stub helper. It'll just already be in data. That's just quickly how that works. This is, I think in the previous slide I talked about the linked edit segment. And so the linked edit segment is super important, but it's not totally like easy to read. Like it's kind of a, you couldn't just parse the Mach0 format to understand what's in the linked edit. But I'll explain a little bit how you can parse it. It has exports, imports, relocations, and like binding information for symbols. This is like super important if you're trying to like figure out like function entry points in the function, or like figure out what the code is actually importing in. So it's great. The first thing you want to do when you're looking at an application is like knowing what it's calling and what the entry points are, so you can kind of try to understand like the inputs and outputs of the program. The one thing you want to know here is the LC code signature. So again, these are all load commands. So as I talked about earlier before, load commands are like the way that the Mach0 is mapped out. And so most of the load commands here don't actually map a piece of memory into code from the kernel, or the kernel doesn't use that to map code into the process. This is just like the metadata that I was describing before. And so there's, besides the LC code signature, there's also the LC data encode and LC function starts. And these are really, really important. If you're ever writing a disassembler, or if anyone's written a disassembler themselves, if anyone's written like a recursive descent disassembler, you would know how important LC data encode is. Basically, it just